Welcome to M2. Today in this video we're going to look at laminas in equilibrium. Now, in terms of the videos so far in this particular series, this is where things start to get a little bit more challenging. And the first thing to take into consideration is that when you have a lamina that is suspended at a point, whether that is hanging freely or fixed, it will always hang so that, if it's freely, its center of mass is vertically below the point that it's either being suspended on or it is pivoting about. So like here, the center of mass hangs directly below where it's being hung from. And the second one, if I've got, say, a pivot, it will hang directly below that pivot. Okay, so that will be then my weight is what's coming off the shape, and then in this one it's going to be the normal reaction. Okay, so in both of these, they're going to be counted, so the tension and the weight in this one, or the pivot's reaction and the weight, these will be equal and opposite. But what's important is that this center of mass will always be directly below this pivot point. So, if I move the pivot point here, then this whole shape will turn so that this is directly hanging below this pivot point. So here we got another one. If I now put the pivot in this position, then what happens is that this will then start to hang so that this is now directly below. So the weight would hang in this direction or point in this direction, and now my normal reaction will be in this direction. And the same scenario exists whether it's hanging, outside like this one, attached to a piece of rope or string or whatever. Okay, but this will always move so that the center of mass is directly below where it's attached to. Okay, now in questions you don't need to kind of redraw it, twist it around like I have shown you here. It is just about drawing kind of straight lines, connecting them to the point where you're pivoting about. Okay, but sometimes for some more complicated ones you might want to do a little quick sketch just to have a little look, as it sometimes helps you visualize it, but that's entirely up to you. Now in this first example we've got an L shape and we're going to hang it from different points. Okay, so it's going to be suspended from different points. Now before I can go ahead and do this, the first thing I need to do is work out where my center of mass is, and I can do that by splitting this L shape up into two rectangles, so either cutting across here or here. Okay, now I'll pop on this missing side here, but either way, if I cut across here I've got these two. If I cut down here, I've got these two for this one and these two for this one. It doesn't really make a difference which one I use. So normally I would probably cut across here because all the values are already given to me, but I'm just going to cut it down for a little bit of a change here. So we've got an area of my first one of 12 and an area here of 4. So first one had an area of 12, and then the center of this would be 1 across 3 up, so 1, 3. My second one has an area of 4, and this is, so we go 2 here and then it's another 1, so it's 3 across 1 up, so 3, 1, and then my total area is 16 and X bar and Y bar. So we've done this before, so I'll speed this bit up. Now we have our centre of mass. And it is 1.5 across. So I'm going across here. This is 2 across. So 1.5 across, 2.5 up. So we're somewhere around here. This will be, my G, my centre of mass. Now, for this first one, it's going to be fixed at A. So if it's hanging at A, what you want to do is you want to draw a straight line from A and through that fixed point, through that centre of mass, your G value there. So I'm going to do this in grey. I'm going to draw a longer line. You don't need to make it super long, but just find it a little bit easier. And now that's the way everything's going to kind of hang. So if you imagine now, my shape is hanging from here, the centre of mass is directly below it, its weight is hanging in this direction. So tension would be going in this direction. And just to show you, I've just spun that shape around there. So this is the scenario that is happening. So we're looking at now the angle the vertical makes with AB. So that's this angle here called theta. Yeah, as this line is the vertical, the downward vertical. So we're looking at this angle here, AB. Now, if I just kind of redraw it for you as a little sketch, we know this is the point A, we know this is the point G. We know it's 1.5 across and 2.5 up, as that were the coordinates. So, thinking of trigonometry, we've got tan theta is opposite over adjacent. So theta is 59.0 degrees. Okay, so first one, nice, easy start. Now, for part B, we're going to hang from B. So this time now we've got it a straight line going from B through that centre of gravity, G. So if I just draw that kind of straight line there, that's what we've got, and, extending that line, I would have my normal reaction would be going in this direction. So that's my normal reaction. This is essentially going to be my weight. And I've just spun it around again just to help you visualize it. Okay, so you can see this is the downward vertical now. It's here, this downward vertical. It's hanging from here. This is my downward line. Now I need to find the angle that this vertical makes with AB, so it's this angle here. Okay, so my original diagram, it's there. And actually, I'm going to get rid of the theta. Let's call it alpha, as we've already used theta as a letter there. So now I need to work out this angle. So again, I'm just going to draw a very quick sketch of that triangle that we're dealing with, and work out my value. So height wise, it is still 2.5, isn't it? But now if I think about the distance is, we got 4 to here and then 0.5. Because this is 1.5 across. Sorry, I said 4, that total length is 4, isn't it? So sorry, my mistake there. So this is 2 plus 0.5. So 2.5, thinking of it like that. Or total length is 4. This is 1.5. 4 minus 1.5 is 2.5. So that distance there is 2.5. And there is my alpha. So again, it is tan. It's opposite over adjacent. This one should be quite obvious that it needs to be 45 degrees. Now, third and final one for this example, we're now looking at E here. So again, same as all the others, I'm going to take my ruler and my pencil and I'm going to draw from E through G and down. And of course that is my normal reaction. I don't need to worry about this normal reaction in these questions at the moment, but I'm just popping it in there just to kind of show you. So here's my new diagram. And as I did before, I've just tilted it round or twisted it round to show it's now dropping straight down. And we want the angle that makes with AB. So I'm going to pop it in here. So let's get on to beta now. A few of you might be thinking, well, is it not this side? In this particular question, I don't think it really matters. I mean, there's nothing to say that it has to be this side or this side. It just says the angle it makes with, that the vertical makes with AB. So I think, you know, in terms of your exam and your working, you know, you need to really clearly label which angle you're calculating here. Now, if I think of so I'll pop it onto this one as well. Now, if I think of this triangle initially here, what I've got this triangle where I'm trying to find this angle here. I know this is 6, but what I don't know is I don't know this length here because I don't know where this line hits AB. So this is making my life a little bit more difficult, okay? Because I know it's going through G, which is somewhere along there. So what I want to do is I want to think about finding another triangle within this. And if I think, well, this side and this side are parallel, okay? So using this angle and this angle must be equal. So what I can actually do, I'll pop this on my diagram in red, is go from this G up to here. Because these are parallel, this is also beta. And because I'm going to the G, then I know what my lengths are. That because this is 1.5 across, this little bit is 0.5, so 0.5 here. And because this is 2.5 high, 6 minus 2.5 will give me 3.5 from the top. So this is 3.5 on here. Now I've got this triangle which is in red, in which I can find my beta. So I've got tan beta, it's opposite over adjacent. And that gives me 81.9 degrees. 3 significant figures there. And that is then my angle. Okay, hopefully that's made sense. What I'm going to do now is move on to a second example, slightly different, before we get stuck into a few questions. Don't forget, if you haven't done so already, to subscribe to the channel. If this video is useful, hit a like, and don't forget, send us some comments with any questions you may have or anything you want to say. Now, centre of mass is really important in these kind of things when we're looking at inclined planes or rough inclined planes. So if I've got this plane here, whatever angle it is, and you can see here that my centre of mass here is hanging down nicely. This shape will sit on this plane. Obviously, depend on how rough it is, it might move, it might not move, but it will just sit on this plane nicely. But as I increase the angle, this weight directly down from the centre mass is always going to hang vertically down, isn't it? So as I increase the angle, this will slowly move over beyond the points of the shape. So in the second one, what's happened here is that I've increased this angle. Let's call this beta, and it's now at a point where the weight coming from the center of mass is going directly through this bottom corner here. So this is essentially on the limit. And in my final diagram here now, my center of mass, the weight that acting vertically downwards, is now outside of the shape. And what this means is that this shape is now going to start to topple. Okay, it's going to start rotating in this direction. Okay, which is a anti-clockwise direction. And that is essentially what we're going to be looking at in this next example. Okay, a lot of these questions will ask the kind of the angle to do with the limit just where it doesn't topple, you know, or where it's about to topple, okay, which is what this center one is all about. Anything then angle lower than this shape will be safe from toppling. Any angle above this shape would topple, okay? And that's how this center of mass, you know, really works. And that kind of is something you can think about in the real world when you talk about, you know, the center of mass of all sorts of things like cars and things like that, and determine whether they would actually topple or not, and how keeping that low, or what they often call it, a low center of gravity, yeah, that low center of mass, that low center of weight, that's where you want, you know, just to minimize the chance. So, you know, if I had that G was down at the bottom here, it's very difficult to topple this shape, isn't it? But if this center of mass was right at the top, then it'd be really easy to topple this shape, okay? Because where this will hang down, once it hangs down outside of my shape, then it's going to topple. So just to kind of reconfirm and just make sure everyone is very happy with this, it's all about this bottom line. So it's all about where this shape is in contact with the surface, yeah? So if, you know, my center of mass and this vertical downward line, if it hangs within the contact area, your shape will not topple. So this is just inside the contact area, it's touching on the end here. So that's kind of at the limit, and this one you can see then is outside of the contact area, which is why it will topple. Okay, so just to kind of clear and clarify that, make sure everyone understands what I mean. Now, in this question, the first thing I need to find is the center of mass of my L shape. Now, we know it's A, B, C, D, E, and F like so, and we know AB is 2, BC is 4, CD is 2, and DE is 2. Okay, I've just kind of used the same or very same one as before, but I'll do it from the start. So I'm going to split it across this way in this one. So I can see I've got, you know, an area of 8 here, and if I look at the bottom, well, I need this is 2, this is 2, so this distance here is 4, so this area is 8 there. The center of this one is going to be 1 across, 4 up, and my bottom one is going to be 2 across, 1 up, isn't it? There. So we've got 8 times 1, 4, plus 8 times 2, 1, and that's 16 x bar y bar. And here's my center of mass, which is obviously the same as, it's the same triangle as we used earlier. And what I want to do is put that on my diagram. So 1.5 across, 2.5 up, so there's my center of mass. Now, if it's the maximum value of theta without it toppling, then looking, this bottom line is where it needs to stay within that, the contact line, which means that my G will have to go through F for it to have a maximum value. Okay, so that is what we're doing. So imagine this, as this is the real scenario that's kind of happening. You know, so on my diagram, obviously I've just drawn it through the F because that's what we're doing. But if I, increase the incline on here so that it drops directly below the F or through the F, this is the scenario that's happening. Obviously, you don't need to redraw a shape, you just need to pop it on your original shape. But just to help you visualize it a little bit better. Now, what we'll need to do next is obviously try to get to my theta, which initially looks, a little bit difficult, but since we know the position of G, that will enable us to find an angle. So if I think, and I'll pop this up in kind of green so it stands out a bit. If I look here, because I know this position of G, I could work out this angle here, which will be the same as this angle because they're opposite. So this angle, let's call it alpha, and let's draw that triangle. So here's my alpha, and I know it is 1.5 and 2.5 because that's F there and that is G on the diagonal. So tan alpha is 2.5 up over 1.5. So alpha is 59.0 degrees to 3 significant figures. Now if I take that to the larger value, the larger triangle, this is going to be 59 degrees, isn't it? So now what I'm thinking of, if I look at that larger triangle, I'll just switch back to black here, just so you can see the difference. We know that's theta, that's going to be 90 degrees, because that is the downward vertical, and this is my alpha. So my theta has got to be essentially just 90 minus alpha, isn't it? Or you can think of it as 180 minus 90 minus alpha, in longer terms. So theta in this case would be 31.0 degrees, again to 3 significant figures. Now you could have actually found it just straight from this triangle, because it would be this top angle is the same as the theta, but I don't think it's as easy to spot. I think it's much easier to look at it this way, which hopefully made a little bit more sense to you guys. Now let's have a look at a couple of questions, and as always I'll pop the answers at the end of the video. So first thing we need to do here is work out our center of mass. Now I'm going to do this by splitting this up into a rectangle and a triangle, as this is now going to be 4 and 4, and that'll just make my life a little bit easier. Area of this first triangle, we got 4 by 6, which is 24, and the triangle is 4 times 4 is 16, divided by 2 is 8. So those are my points. Looking at the rectangle, it's 6 across, so we're going to go 3 across, 2 up. So 3 across, 2 up. And then my G2 is worked out with the coordinates of each of these points. So this first point that I've just marked here is going to be 6, 0. This one is at 10, 0, and R here is at 6, 4. So for G2, we want to add up our X values and add up our Y values and divide by 3. So 24 over 3 is 8, and 4 over 3 is So that's my G1. Now I've got the 2, I can go ahead and work out where the full centre of mass is. So we've got 24 times 3, 2 plus 8 times 8 and 4/3. And that's going to be equal to 32 x bar y bar. So we've got 24 times 3 is 72, and then we've got 48. 8 8 are 64, and then 8 times 4 over 3 is 32 over 3. And all I need to do now is add these up and then divide by my 32. And that means we've got roughly 4.3 across, so this total is 6, so just over halfway there, and 1.8 up. So something like that for our main, or our centre of mass of this whole shape. Now, although I've done the rounded values here, just so I can roughly get this in the right place, I'll use the full values in all my calculations moving forward. Finally, as I almost forgot, we need to make sure that we say that these are our distances from P, just so that we are clear where we're working it out, or where we set as the kind of origin point. Now for part A, we want to essentially attach it at Q. So thinking about this now, you know, it's just a straight line from Q through my centre of mass. So that is now my vertical line. And we're looking at the angle that makes with PQ. So I'm going to start off with calling that one theta. So just remember now, you know, you can visualize it turning around, you can turn your paper around in the exam, you know, just to try and help you visualize it better. You know, rather than redraw it out, probably turning your paper around, you know, if that helps, go for that. Now, obviously we know the point G, so we can work out this kind of triangle. So we've got G here, Q here. That's my theta, and this side here, which we've got here, well, we know it's 69 over 16, this distance. So I'm going to put it in as 10 minus 69 over 16 there. And the height is 11 over 6. I don't need to worry with that one. So that height is the same, but when I'm looking at this distance, it's 10 minus this distance, yeah? So that gives me, well, it's tan, isn't it? So tan theta is opposite over adjacent. And that gives me 17.9 degrees. And that's the 3 significant figures. Now, part B is going to be attached at Q. So, sorry, it's going to be attached at P. So all we need to do now is again draw our straight line from P through G. And since it tells me that it's again, you know, the angle it makes with PQ, so that's the angle I'm trying to find there. So again, it's just a matter of a diagram. Here's alpha. This one now is 69 over 16 as we're going from that point, and our height is 11 over 6. As when I did these earlier, you know, I went from point P. Don't think I actually said that though, but that's what I was doing. Anyway, so tan alpha is 11 over 6 over 69 over 16. And this is 23.0 degrees, again to 3 significant figures. So finally, we are now attached to point R. So this time we get this line. Okay, and I just make sure that line goes through PQ, and this is the angle I'm gonna find. Okay, so I'm just stating that on my diagram, making it nice and clear. Okay, very important there, nice and clear, so that we can, we can just go ahead with our calculations there. Looking at the diagram, let's go with the top angle here. So we know that this is also beta, and this will be the easiest way to find because we know exactly where R is. Okay, so if I think of that top triangle first, let's draw it as shown. So that's R, that's G, that's beta. Well, this is going to be now 6 minus 69 over 16, isn't it? Because 69 over 16 is to here, but this full distance is 6. So this is 6 minus 69 over 16, and this height here is 4 minus 11 over 16. So 4 minus 11 over 16. So we got tan, beta again, opposite. So 4 minus 11 over 6, don't know what I was saying there. And then 6 minus 69 over 16. And that'll enable me to find beta. And that should give me the angle of 52.1 degrees. Again, the 3 significant figures. Okay, so I've just clearly labelled my diagram, and knowing obviously that these are parallel lines here, that we can state that these two angles are the same. So again, here, first thing to do is to find that centre of mass. So we've got A, B, C, and D. And A to B is 3, C to BC is 2. So centre of mass here, G is obviously going to be 1.5 and 1. Nice and easy. So pop it onto the actual diagram, and then I want to draw my line from that through the point D. Because that is when it's raised up, that'll be the point where it's about to topple. So when that is going through that, because as soon as this line goes through this line, it's going to topple. It has to go through this bottom line. Okay, so when this theta is maximum, this is going to raise up, and this then is going to eventually go through this point D, which is what I want to find. Now I've just popped on here a quick sketch just to kind of show you, to visualize it. Sometimes with these, when I'm looking at this diagram, sometimes it's totally messing with my mind, and I need to do a quick sketch just to kind of see what's going on. So I like to find this angle here first. Okay, obviously you can go ahead and actually just straight find this angle, because this angle and this angle are going to be the same, because this triangle and this triangle is a similar triangle. Okay, but I'm going to stick with this way, as it's the way I can visualize it better, So we know that this is G and this is point D, and we know that it's 1.5 across, 1 up, so tan alpha is 1 over 1.5, as it's opposite over adjacent, and that gives me 33.7 degrees to 3 significant figures. And then that means that looking at my theta, my theta is basically 90 minus alpha. So 56.3 degrees, again the three significant figures. And that is my final answer there. As I said, don't forget you could skip this step and realize that this is theta the same as this. Okay, so you can just jump straight in with finding this angle, which would be the tan theta is 1.5 over 1. So that is your alternative method there. In fact, let me just write down and show you that alternative method. So in the alternative is recognizing that this angle here that I put in purple is theta. So when you draw on this angle out, or this triangle, you've got your alpha there. We've actually got your theta there, haven't you? And that is G, and this point was D. And then you've got 1.5 across and 1 up. So this time, you know, your tan theta is opposite, which is 1.5 over 1. And then you'll get your 56.3 to three significant figures in one go. Okay, so you can do that. It's just about spotting it and making sure, you know. So sometimes you'll see this in, if you're doing past paper questions, you'll just see them do this angle as equal to this one. It can get confusing when you first see it, but you can see that these triangles are the same. They're similar. Now, with this question, we're bringing mass into the equation. Okay, and there's two kind of ways you can do it. You can work at the center of mass first and then apply the masses and work out from there, or you can do it in one go. So let's do it kind of the longer way first, as you know, that often is easier for people, and then we'll look at the kind of shorter way of doing it in one go. Now I'm going to split this shape up as follows. That gives me an area here of 30 and an area here of 10. And my center of mass is going to be, so of these two rectangles, 1.5 and 5. And then for my second one, G2 is 5.5 and 1. So this means we've got 30 times 1.5 and 5 plus 10 times 5.5 and 1, and that's going to equal 40 x bar and y bar. And here we have our center of mass of the actual shape, L shape, the lamina. Now in terms of mass, we've got one mass for the lamina, so that's at 2.5 and 4. We've got our 0.2 m, and that is attached to point D, okay, which is here, and D is going to be 3 across, 2 up, isn't it? So 3 across, 2 up, and that's going to equal 1.2 m x bar and y bar. Now quite clearly the m's can cancel all the way through there. You know, we don't have to kind of worry about those. So these now are my new centers of mass. Okay, I can take them over here, and that is what we've got. So just putting these out here in decimals so that we've got just like a rough idea of where they should be in terms of my shape. But obviously I'll use the full values there. Now, before we go on to the second part, the main part of the question, let's just look at how we could get to these values just in one go. So what we could have done is, if I split it up the same again, we know this is 30, we know this is 10. We know this total weight here, or area here is 40. So what I can see is that this is 30 over 40, or 3/4, and this one is 10 over 40, which is 1/4. So what I can say is that this would be 3/4 m, and this is 1/4 m. Okay, remember it comes from the 30 over 40 is obviously my 3/4, and 10 over 40 is my 1/4. Okay, so that's how I could approach it. So I can go now with 3/4 m, and that is, again, you know, it's going to be at the 1.5 and 5 here. So 1.5 and 5 plus 1/4 m, and this is going to be at my 5.5 and 1. And then we've got our 0.2 m, which is the weight that's been added to D, and that's at 3.2. Now my total mass here again is 1.2 m, x bar and y bar. And as before, I've got m throughout, so you know I can divide through by m and just kind of get rid of that, make my life a little bit easier. And at this point you can now kind of see that you've got the same set of values as we just had. So this is going to give me 31 over 12 and 11 over 3. Okay, so hopefully that made sense, and that would be a shorter way of doing it. You're just using, you know, the areas in their ratios compared to the whole value there, the whole area, and you can use that then to do this in one go. So back to finishing off the question. So we've got our point G here, 2.6 across roughly and 3.7 up. So I've marked like a rough idea of where it would be. It's suspended from from E. So I've got to go through E and through G, and we actually want the angle that it makes with EF. So we're looking at this angle here. So thinking about this kind of triangle, if I take my E to G and take that kind of straight up, that's the angle we're looking at there, aren't we? And we know the kind of distances involved. So we know where G is, and we know that this is total distance is 3, so 3 minus my 31 over 12, because it's 3 minus 31 over 12. And then the height is 10 minus the 11 over 3. So 10 minus 11 over 3 for that height there. So tan theta is opposite, 10 minus 11 over 3, over adjacent, 3 minus 31 over 12. And that gives me 86.2 2 degrees to 3 significant figures. We often do angles to 3 significant figures, just in case I haven't said it before. So here we have a triangle of mass M. AB is 7 and AC is 8. We've also got a 0.3 M mass attached at C. So we got that 0.3 M attached there. Assuming that the lamina does not slide, calculate the maximum value, blah, 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 blah. So let's find the centre of gravity, centre of mass for the triangle. So let's think of the triangle first. Looks like so. And the triangle's centre of gravity here is all about, we'll do it from obviously point A here, with 7 and 8, B and C. So my G1 is going to be 0, let's do them, so 0, 0, we've got 7, 0, and we've got 0, 8. So it's 0 plus 7 plus 0 over 3. And then we've got for y, 0 plus 0 plus 8 over 3. So it's 7 over 3, 8 over 3 for my G1. Now let's think about where we are in terms of the masses. So we've got M times 7 thirds and 8 thirds plus 0.3 M. That's at C, which is 0 cross 8 up, which means we've got a total of 1.3 M at X bar and Y bar. And as before, we can cancel these M's, divide through by M, as that is, you know, they're in everything there. So now I've worked that out, I can roughly plot this point on my diagram, but I will always use these two values. And there we have it, a 1.8 across, 3.9 up, somewhere like that. And then we're going to join that through A. Okay, because A is that point furthest down the kind of rough plane where my AB is still going to be touching that plane, because that's obviously the important bit, you know, where this is still touching, going through there, because we don't want it to topple. This should now be quite straightforward. So I draw this triangle, and let's draw it nice and big. That's my A, that's my G. That's kind of my alpha. And if you remember, if this is alpha, this is alpha, so this has to be theta because it's a similar triangle. And my X value is that 152 over 39, and then the height to G is my 70 over 39 there. So let's go straight in with tan theta is going to be opposite over adjacent, so it's a 7 there. And that gives me 65.3 degrees to 3 significant figures. Hope you enjoyed watching. Don't forget to subscribe. If you have any questions, pop below. And even if you spot a mistake, let me know so that I can correct them. Okay? Brilliant. See you soon.